Okay, so it says an empty train car moving at a speed of 15 meters per second collides with a loaded car of 3 times the mass, moving in the same direction at one-third the speed of the empty car. The cars stick together. Find the speed of the cars after the collision. This is important. Reading the word problem is the most important step. From this word problem, I can identify two objects. Okay? I find the empty train car to be one of my objects, and I find the loaded car to be my second object. So I'm going to establish a difference between the two objects. This is going to be my object 1, and the loaded car is going to be my object 2. Okay? This is the first thing that we need to do. We need to identify where the objects that are part of the problem. We will also do the same separation in the givens. Okay, I'm going to start writing my givens, but I will separate all the information. So I have one object and I have my second object. The first object is the empty car, and my second object is the loaded car. Okay, that's my first difference. Okay, now what do I know about the empty car? Well, I know it's empty, okay? But what else the exercise tells me? About the empty car, it says that it is moving at 15 meters per second and then it collides, okay? So with this, moving at 15 meters per second is telling me the velocity of my object 1 under the initial condition. Initial because it is before the collision, okay? It is 15 meters per second. Now it says collides with a loaded car. This loaded car is 3 times the mass, 3 times the mass, moving in the same direction at one-third the speed of the empty car. So, if you read this problem carefully, you will see about two objects, okay? But then all the information about the loaded car is given in comparison against the empty train car, okay? About the mass, it says that the mass is 3 times the mass of the empty car, okay? So, about the loaded car, I know that the mass of my loaded car is 3 times the empty car, okay? I know that. That's what the problem is telling me. Now, I don't know what is the mass of my empty car, okay? I don't know what is the mass of my empty car. So, I say that my mass of my empty car, I will call it with a variable. Vamos a usar variables like it is math class, okay? Like this is algebra class. I'm going to call the mass of the empty car with a letter. Now, that letter, I like it to be M because remember, M is mass, okay? So I'm going to use this variable. M is the mass of my empty car. But the loaded car, it says that the mass is 3 times the empty car. Okay, so it's going to be 3, and the mass of the empty car that you know we're going to be using a letter 3m. So the empty car is going to be a mass m, and the loaded car, which is three times the mass of the empty car, is going to be 3m. We are translating sentences to algebraic expressions. That is something that you are already familiar with, but not in physics. In physics, you are more used about writing the givens and use them in a formula. In this case, it is a special case, so we're going to be using letters. Okay, we're going to use letters to express the unknowns. Now, about the loaded car, it says that it is moving. Okay, the loaded car is moving. It's not a rest. It says it's moving. Okay, in the same direction. In the same direction as the train car, the empty car. But then it says at 1/3 the speed of the empty car. So we need to translate all that sentence into an algebraic expression. So 1/3, you know, it is a 1/3, it is a fraction. So you can write 1/3 like this. So the speed of the loaded car, it says that is 1/3 the speed of the empty car. I can write it in words like this, but then I need to substitute. Angie, can it please turn the cameras on? Thank you. So I will substitute by the information that I have. Okay? The velocity of my loaded car is 1/3 the speed of the empty car. If you check the data that we have, the speed of the empty car is 15 meters per second. So I will substitute here. And this will give me how much?
5.
5 meters per second. So take a look. Even though the problem didn't tell me that the loaded car was traveling at 5 meters per second, by just reading all the information in an algebraic expression, you can get a value from that. Okay? So remember what we need. We need to know masses and we need to know velocities. Okay? We need to know masses and velocities according to the formula that we need to use. So I have velocities, I have the masses, so that means that I can start by using that formula. Now, what am I looking for? We need to read this. Okay? It says the cars stick together. If the cars stick together, we know that this is inelastic collision. But then the most important part says, find the speed of the cars after the collision. I need to find the speed. Okay, I'm looking for a velocity. But then it says after the collision. After the collision tells me about a final condition for velocity. That means that I'm going to look for the final velocity of the two objects. So this is what I'm going to focus on. That's what I'm going to look for. Okay. So I begin by writing the formula. Okay. Momentum of my empty car plus momentum of my loaded car equals the final momentum of the two objects. I substitute by the givens and I'm gonna look for the final velocity. This is going to be my unknown. So because that is my unknown, I will start by substituting all the values. Remember, this is my empty car, this is my loaded car, and that's how I'm going to introduce all the data. Now, the mass of the empty is just the letter M, okay? And the velocity of the empty car is 15 meters over second, plus the mass of the loaded car, that is 3m, multiplying the speed of the loaded car, that is 5 meters over second. All this is equal to what I have in the right. Mass 1 plus mass 2, my mass of my loaded car, the empty car, and the mass of my loaded car. So this will be m plus m2, that is 3m. And all this is multiplying what I need to find, that is final velocity. Now, take a look. These m's are variables. Okay, those are variables. But then you notice that meters per second also has m. So because it is very confusing to work with similar units, okay, for now, I totally suggest and recommend to ignore the units. Only for this type of exercise, ignore the units and focus only in the process, okay? Ignore the units in this moment. Now, we're going to rewrite the expression. M times 15 is going to give me 15m plus okay, 3m times 5 is gonna give me also 15. But I also need to write the variable. All this is equal to what I have in the right. Okay? Now take a look. And this step is very important, so take a look. In math, in algebra, when we have the same variable repeated in different terms, we call it like terms because they share the same variable. Okay? When a variable is repeated in different terms, we call them that they are like terms. So what happens when you have like terms? Example, 2x plus 5x. What do you do if you need to add this expression? What is the procedure that you do?
You add the numbers and just copy the variable.
You add the numbers, 2 plus 5 is 7, and you just copy the variable. That means that x is going to be written once. We're going to do the same here. This is the same procedure, okay? We have a variable repeated in the two terms, so we're going to add the numbers and copy the variables because they are like terms. Okay, so 15 plus 15 gives me 30, and you just copy the variable, 30m. Now, you continue writing the expression, but you notice also that in here, again, you have like terms. So, what happened in this part? You have to do the exact same. You're going to add the coefficients and write the variable. Now, remember that when no coefficient is next to the variable, it is invisible 1. So in the end, what you do is invisible 1 plus 3 gives me 4. And you just copy the variable m. And all this expression is multiplying the final velocity. Now, because I'm looking for final velocity, I will isolate for it. What I do is I need to get rid of 4m. Okay? 4m is multiplying, and to get rid of it, what I have to do is I need to divide by the same expression. Okay? So I'm going to divide all my expression by 4m. So let's see. Okay, that's what I have. This allows me to cancel 4m with 4m. Okay? But if you also notice here, you can also get rid of the masses. You can get rid of the variables m and m are doing opposite operations, so that means that you can cancel them. How much is 30 divided by 4?
7.5.
Now, this is equal to final velocity. Now, what units do we need to write right here? What units do I need to write?
Meters per second.
Meters per second. Take a look. Here, remember that we said that we are going to ignore the units. But the units don't disappear, okay? Just because it is more comfortable to work like that, we decided to ignore the units. But in the end, you are going to write them. You're going to bring the units back. So in the end, 7.5 meters per second is the final velocity of the entangled mass. Now, tell me, how difficult do you find this exercise? Can you write it in the chat? Yeah, it's easy. It's easy. The only thing is that you just have to write the unknown in terms of variables and work like if it was a math problem. That's the only difference. But the rest is just applying the formula. Okay? And applying algebraic concepts like when you have like terms, you add the numbers, but you just write the variable. Okay, you don't multiply the variable or you don't multiply the coefficients. Okay, so there's There are a few rules that you need to follow. It's not too complex, okay? It was just a review exercise, but for you to know that sometimes the givens are not written in numbers, are written in sentences, so you have to gather all the information from those sentences. That was the idea of bringing this problem to class. If you have a doubt in this exercise, you can ask me in this moment. In the chat, if you don't feel confident to unlock your microphone. Ready?
Miss, on the formula, on the very first step, 1 and 1 plus 2, we always represent the mass.
Yes, in the beginning of the formula here, 1 plus 2, it refers to the object 1 plus object 2. That's what it means. Okay? Object 1 plus object 2. But what you add are just the masses, okay? Not the velocity. The velocities are the same. That's why it is just written once. Okay. So the class that we're missing, remember that last Monday I didn't give you the classes, okay? So I didn't tell you in which day we were going to recuperate this time, okay, this class. So that time is going to be tomorrow afternoon. Tomorrow by 2:30, okay? 2:30 p.m. tomorrow. Physics class, okay? Physics class tomorrow at 2:30 p.m. Now, it is going to be a class and it's going to be more about practice. Okay, so I will introduce a new topic, only the theory, and tomorrow in the afternoon I will continue. Okay, I will continue with this topic. It is related. Okay, remember that there are two kinds of collisions. We have inelastic collisions, like the one that we just saw, but we also have elastic collisions. Now take a look to this example. When a player kicks a soccer ball, the collision between the ball and the player's foot is much closer to elastic than the collisions that we have studied so far. Okay? What is the difference? In this case, elastic means that the ball and the player's foot will remain separate after the collision. This is the main difference between elastic and inelastic collision. In inelastic collision, after the collision, we have an entangled mass. The two objects, okay, become one object in the end. But in elastic collisions, the objects remain separate after the collision. Imagine a baseball event, okay? So, what happens when a bat hits the ball? Okay, the ball just runs away from the bat. They don't stick together after the collision. So when this happens, we're talking about examples of elastic collision, that two objects remain separate after the collision. So in an elastic collision, two objects collide and return to their original shapes with no loss of total kinetic energy. After the collision, the two objects move separately. In an elastic collision, both momentum and kinetic energy are conserved. We're going to discuss about conservation later. So to define what an elastic collision is, I would say that yes, there is a moment where the two objects crash, okay? But in the end, what happens? The two objects are not going to stick together. They will be separate after the collision. And another important thing is, it says they return to their original shapes. That is important because that means that the objects are not going to be deformed after the collision. In elastic collisions, that's why it is elastic, they return to its original shape. When have you watched Captain Subasa, or in Spanish it is Supercampeones? So when a player so good like I forgot his name.
Oliver?
Oliver, yes. When Oliver hits the ball, you can see that the ball is deformed, okay? You know the balls are very round, but in Supercampeones, when they hit the ball, okay, so that's the leg, okay, the foot, and this is the ball. But after they hit the ball, the ball is it is deformed. It looks more like that, okay, more like an American football ball. But that's just the animation, okay? But in real life, it happens too. The objects are deformed. But after the collision takes place, after they kick the ball returns to its original shape, okay? So once the ball is kicked, it's round again. This is an example of elastic collision. The objects are not deformed. So if I need to write two characteristics of elastic collision or two differences between elastic and inelastic is the objects remain separate after the collision. Separate. Okay? After the collision, the objects remain separate. And number two, objects are not deformed. Those are two characteristics. Okay? Two characteristics. And that's why the word elastic is important. Because no deformation occurs. Now, by definition, this is the definition of elastic collision, is a collision in which the total momentum and the total kinetic energy are conserved. So if I ask you what is conserved in an elastic collision, you will say momentum and kinetic energy. And this is how you express the elastic collision, okay? Conservation of momentum, that means momentum initial equals to the final momentum, and conservation of kinetic energy. Kinetic energy initial equals kinetic energy final. So we're going to have two expressions, one for momentum and one for kinetic energy. But we're going to discuss about it in the class tomorrow, okay?